The final component of our three-dimensional T and B frame is that we're going to define the binormal vector as the cross product of the unit tangent vector and the unit normal vector. So that we know, for example, this vector is orthogonal to both T and N because it's a cross product, okay? And we're able to say then this creates a right-hand coordinate system where I have the tangent vector, the normal vector orthogonal to it, and then this binormal vector that we're now talking about. So that we're able to create a T and B frame, and then the rate at which a curve comes off of the plane, the rate at which the curve leaves the plane. Okay, so that if we're able to have this just a two-dimensional vector in the plane, then there's no torsion because we're not moving off the plane in any way. Whereas if in an example of a trajectory that's going to come up into this plane and then go off of it, that there is a certain amount of way that this curve or trajectory is going to move off that plane, and we're going to call that the rate at which this binormal vector changes with the arc length. Okay, so that we can then just talk about this in talking about its components, the cross product, and that by the rules of the cross product, I would say that this is TS crossed with the normal vector plus the crossed with the change of the normal vector with this. And this is just the product rule for derivatives. Okay, so that expression now is that change in the binormal vector with the arc length. Okay. So that we know that the normal vector that we just found out is the curvature times the change on the tangent vector with arc length, and that the normal vector and this change of tangent with arc length are scalar multiples. Okay, so we know that when we're talking about the cross product, that if we have scalar multiples, then therefore that we have that cross product being 0 with scalar multiples because they are in that way. So that we can then write, so if N and TS are scalar multiples, this, and this are going to scale to 0. We cancel that out so that then we can finally write that binormal vector change with arc length is the cross product with the tangent, unit tangent, and the change of the normal vector with the arc length. Okay, so that begins us kind of starting to talk about how we want to do it, but so that this is this change, and what we want to do is be able to figure out how or how much or how fast is that we can define those leading terms as this Greek letter ta, which is we're going to call the torsion, and end up with an expression in a similar way for that change. Okay, so ta equals a torsion. Okay, so that's a measure, a scalar measure of how fast this curve or this trajectory is coming out of the plane. So if we kind of do a little bit of arithmetic and we can find out that that torsion value is the opposite of that change times the normal vector. Okay, where B is our usual definition of T cross N. Okay, so that gives us a way to calculate the binormal vector and being able to describe its magnitude with this value torsion called tau. Okay, and we call that, okay. So then what I want to do is just take an example of this and look at what happens with a vector that we're going to, let me just turn this one off here, and then we go back to that one. And so that now when we talk about an example, we're just going to take a circle. Okay, and a circle in a plane, obviously we've done this quite a few times, is that generic radius r cosine sine, letting t go from 0 to 2 pi, okay, and r is positive. So that you can think about that, well, in the xy plane, so that if I take my normal plane and talk about the x and the y component and then the z component, is that I'm talking about a circle in the xy plane, right? So that I'm in this plane here and creating a circle, in that plane. So let me just change the color a little bit, and I'll draw a circle. And so that value, right, is not going off of the plane. If I were to turn that plane almost flat, you'd see that I'm just going to lay on it. There's nothing below it, and there's nothing above it. So that when I calculate this, I should be able to do find out that the torsion is 0. So that if I look at the value of the binormal vector, that I'm going to use my right-hand rule and find out that this vector is going upwards, this binormal vector going in the z direction. Okay, so that I find out that then that change, dB of ds, is not going to go make any movement in this direction or below, and so that's going to be 0, so then tau is 0. Well, that's exactly what we expected, no movement off the plane. Okay, so a simple circle off the plane. So that the simple circle is just going to stay where it is and not do anything. Well, let's look at another one that we know is going to go off the plane, and that's going to be our high helix. Okay, so we saw the helix just recently and talked about it as the vector now is having a circle in the xy plane, a sine t, and then moving off the plane with b, where t is positive and a is a positive real number and b is a positive real number. Okay, so let me just fix that a little bit. Okay, so that now when we calculate the velocity, of course, and the similar calculation that we did before, and find out that the magnitude again is t is the root, okay, and that the unit normal vector is, or unit tangent vector, excuse me, is this one that we saw in another example. Okay, so that again the denominator is a scalar, so that we don't have any quotient rule when we go ahead and compute the pieces we need for the unit normal vector. Let me just write down the definition here again, and that the magnitude of that change, and we end up with minus cosine t minus sine t and 0. Okay, so that now we have the two pieces we need to calculate the binormal vector, because then now we'll go ahead and say that the binormal vector is the tangent crossed with the normal unit vectors. And I'll just do the quick setup here, 1 over the root for the denominator, and then I, j, and k for the three components. Let me just jot this down, and then b minus cosine minus sine and 0. Okay, so that once you clean all that up and find out that this binormal vector is then going to be the three components, b sine t minus b cosine t, and a at the end here with the denominator of the speed. Okay, a squared plus b squared. So now all I did was just talk about, let me just put down this rule here that we used, and the rule is that, here, let me just put it down here, the rule that I used to compute that was that a of t cross n is a of t cross n. Okay, that's just one of the rules with the cross product. Okay, so now we have an expression for b. That's this here. Okay, so what I'm going to do is I'm just going to change pages once again here, and then we'll look at that vector with difference, right? So let me just copy that down again. So what we did, I just computed, was that the binormal vector is the vector b sine t minus b cosine t and a all over the speed of a squared plus b squared. Okay, so now what I want to do is compute that change of that binormal vector with arc length. Okay, so I know that that is the change with arc length using the chain rule, and so that then that change of arc length dB ds is the ratio of those two, the change of the binormal vector with time over the change of the arc length with time. Okay, so but we already have defined what the change of arc length with time is. That's just the speed, right? So that we can write this as the first derivative of position, and then you go through the arithmetic and we find out it's a squared plus b squared. No surprise there, really. So then I can go ahead and say, okay, well, if I compute this binormal vector with range, I'm going to get let me just copy down the definition here again, the change with time and the change of time. And that is going to be b cosine t, b sine t, and 0, right, from taking the derivative here. And then the new denominator is going to be a squared plus b squared. Okay. So that what we want to do then is then compute tau. That is then the minus dB ds dotted into the normal vector. Okay, so we end up with b cosine t, b sine t, and 0 over this denominator. And then we dot that into minus cosine t, minus sine t, and b for that. And then end up with dotting our b, if we do the calculation, we'll end up with b cosine squared t for this term, and b squared sine t for that term, or b sine t. So we end up with b over a squared plus b squared. And that is our torsion, tau, that is telling us that this is a constant rate of coming out of that plane, constant rate. And we kind of saw that when we were looking for this, looking at this rather, there's y and there's x, looking at the spiral that keeps coming up at a constant rate. And so that we can call this torsion the value that this vector is moving off the plane. So if we create a plane here in the z-axis, so z is z0 somewhere, is that we can measure how fast this vector, this trajectory is coming off of that plane there, right? So as I'm going off of that plane, I can measure how fast that's happening with this constant rate of b over a squared. So now we've completed the three-dimensional vector, or three-dimensional vector system, really, where we have a right-hand system, so I cross t into n and create b, right? So a right-hand rule gives me the vector, and that I then can have this frame move with an object that's moving through space, okay?